The Pilgrim 1 spacecraft of NASA currently holds the record for the farthest distance traveled by any human-made object. It has fascinated people across the globe for nearly 50 years. Since its launch, Voyager 1 has relayed vital data from the furthest parts of space, expanding humanity's understanding of the universe. However, the spacecraft's ongoing transmissions have recently faced strange anomalies that have left scientists puzzled. These mysterious signals have ignited intense discussion, making the scientific community question whether these anomalies are simple malfunctions or signs of something much more extraordinary, possibly even extraterrestrial activity. Join us as we investigate these puzzling signals and explore what could lie hidden in the vastness of space. The human desire to discover the unknown has always been the driving force behind space exploration. This deep-rooted curiosity led to the creation of ambitious objectives like Pioneer 1 and Explorer 2, which were among the most daring space missions of their respective times. On August 2, 1977, the launch of Explorer 2 from NASA's Kennedy Space Center marked the beginning of a transformative period in space exploration. Shortly afterward, on September 5, 1977, Explorer 1 was launched, setting off in a direction that would eventually lead toward the planets in outer space. It significantly modified its orbit, and the results of each of these two spacecraft had a purpose. Weighing roughly 7,720 kilograms, the size of a small car, Explorer 1 and Explorer 2 traveled in separate directions at varying speeds. On December 15, 1977, a key milestone was achieved when Explorer 1 outperformed its sibling in distance traveled due to the different routes they followed. Since that time, Explorer 1 has demonstrated its value as an invaluable tool in broadening our understanding of the universe, offering insights that have transformed how we perceive space. Before we delve into some of its most recent groundbreaking findings, let's first review some of its earlier major achievements. In 1978, while situated around 265 million kilometers from Earth, Explorer 1 successfully captured detailed imagery of Jupiter. By January 1979, the spacecraft finished a remarkable 100-hour mission, producing a time-lapse video showing the rotation of Jupiter. This series of 3,750 images provided unprecedented views of Jupiter's chaotic atmosphere and intricate features. During this mission, the spacecraft also discovered a previously unknown ring encircling Jupiter and identified two new moons, significantly enhancing our comprehension of the complicated gas giant system. To ensure its safe journey and avoid potential collisions with Titan, one of Saturn's moons, the spacecraft carried out a number of correction maneuvers. Following this, the focus of the mission shifted beyond our solar system's planets, as the spacecraft was redirected toward interstellar space, traveling at an astounding rate of 325 million kilometers per year. In January 1990, Explorer 1 embarked on its mission to explore interstellar space, continuing its journey beyond the solar system. During this phase, the spacecraft achieved a number of impressive milestones, including the discovery of 4 additional moons, Mimas, Enceladus, Tessis, and Rhea, and capturing some of the most iconic images of our solar system's outer regions. On February 14, 1990, at a distance of about 6 billion kilometers from the Sun, Explorer 1 took its famous family portrait, capturing stunning photographs of the inner planets. This collection of 60 images joined the spacecraft's portfolio, which also included 670 images taken during its flyby of Neptune. Explorer 2, meanwhile, also achieved impressive milestones during its mission. It recorded wind speeds that exceeded 13,100 meters per second, the fastest winds ever recorded in the solar system, providing scientists with essential data on Neptune's distant atmosphere and its moon Triton, which has surface temperatures that plunge to a frigid -391 degrees Fahrenheit, making it one of the solar system's coldest regions. Triton also displayed ice volcanoes ejecting nitrogen gas and frozen particles up to 5 kilometers high, offering an exciting new perspective on the moon's features. These extraordinary discoveries have greatly expanded our understanding of the diverse and dynamic environments in the outer reaches of the solar system. The contributions of both Explorer 1 and Explorer 2 have been nothing short of groundbreaking. Their missions uncovered previously unknown details about the moons of Jupiter and Saturn, which had previously been thought to be dormant. These findings reshaped our understanding of the geologically active nature of these moons. Explorer 2 made history as the first spacecraft to fly by both Uranus and Neptune, an achievement that has yet to be repeated. NASA employed a variety of innovative strategies to extend the missions of these pioneering spacecraft, such as terminating non-essential systems to conserve power. The mission is expected to continue until 2030, marking the beginning of a new era for engineers and researchers who have dedicated themselves to this extraordinary journey. The designs of Explorer 1 and Explorer 2 showcased cutting-edge engineering. These spacecraft were built to rotate slowly, minimizing image blurring as they traverse space. Before reaching the outer planets, the spacecraft began transmitting detailed images of Jupiter, revealing its swirling clouds and iconic Great Red Spot, a massive storm that has intrigued scientists for decades. However, the most exciting discovery came with the detection of currently active volcanoes on Jupiter's moon Io. The spacecraft's instruments detected unusual signals from the moon, later confirmed by images showing towering volcanic plumes and a surface marked by intense eruptions. One of Io's volcanoes erupted with a force 1,000 times more powerful than Mount St. Helens, covering an area nearly as large as France. As the spacecraft continued their journey, they were eventually powered down to conserve energy before starting their voyage into the interstellar void. Mars and Mercury were not included in the image capture due to technical limitations. NASA later launched other notable spacecraft, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11 to become the most distant spacecraft from Earth. Despite this, Explorer 1 continued its solitary journey for an additional 14 years before it finally entered interstellar space on August 25, 2012. The success of these Explorer missions was largely due to the innovative use of gravity assist maneuvers, which helped propel the spacecraft to their destinations while conserving fuel. Rather than relying solely on their propulsion systems, the spacecraft utilized the gravitational pull of planets to increase their speed. This technique allowed them to cover vast distances without depleting their fuel supply. These included magnetometers, plasma detectors, cosmic ray sensors, and imaging systems, all designed to gather comprehensive data about the environment beyond Earth. These instruments enabled the detection of charged particles, magnetic fields, and radiation levels across different regions of the solar system and beyond. One particularly significant discovery came from the cosmic ray sensors, which recorded fluctuations in high-energy particles originating from outside our solar system. These findings provided direct evidence of the heliosphere, the vast bubble-like region of space dominated by the solar wind, and its boundary, known as the heliopause. When Explorer 1 crossed this boundary in 2012, it officially became the first human-made object to enter interstellar space, offering invaluable insights into the transition from solar to interstellar influence. Over time, data from the spacecraft revealed that cosmic rays are more intense beyond the heliopause, confirming theoretical predictions. This information has major implications for future deep space missions, especially those involving human travel beyond Mars. As the spacecraft moved further into interstellar space, scientists began to notice anomalies in its telemetry. The data packets occasionally contained irregular signal patterns, ones not caused by solar activity or expected cosmic interference. These patterns, though faint and infrequent, did not align with any known phenomena, prompting extensive analysis. Some scientists theorize these anomalies could be attributed to the spacecraft's aging systems, such as degradation of onboard hardware or minor software glitches. Others suggest they might be the result of unknown cosmic phenomena, like interactions with dark matter or exotic forms of energy not yet fully understood. However, a small yet growing faction within the scientific community has dared to consider a more extraordinary possibility: that these anomalies may be signals, intentional or unintentional, from extraterrestrial sources. This notion, while controversial, cannot be dismissed outright. After all, the Voyager spacecraft carry with them not just tools of measurement but symbols of humanity's outreach, a cosmic greeting in the form of the Golden Record. Should an intelligent civilization encounter and understand this artifact, it would represent a first step toward contact. To investigate further, NASA and partner institutions have launched new initiatives to analyze the incoming data using advanced AI algorithms. These systems are designed to detect patterns and correlations too subtle for humans to recognize, potentially shedding light on the true nature of these strange signals. Meanwhile, back on Earth, the legacy of Explorer 1 and Explorer 2 continues to inspire generations of scientists, engineers, and dreamers. Their journeys remind us of our small yet significant place in the cosmos, and of our relentless drive to explore the unknown. Whether these anomalies turn out to be mere malfunctions, natural cosmic phenomena, or the first whispers of contact from an alien intelligence, the missions of Explorer 1 and Explorer 2 have already reshaped human understanding in profound ways. And as they drift silently through the cold, endless expanse of space, carrying with them the hopes, questions, and essence of a curious species, one cannot help but wonder, who, or what, might one day answer? Plasma wave detectors and imaging systems provided critical data on space phenomena. For instance, The magnetometers offered valuable insights into the magnetic fields of Jupiter, Saturn, Uranus, and Neptune, revealing the interactions between these planets and their environments. The plasma wave detectors helped us understand the behavior of solar wind and its effects on planetary atmospheres. One of the most remarkable accomplishments of the Voyager missions was their ability to measure the boundary of the heliosphere, a region filled with solar particles and magnetic fields surrounding our solar system. As Explorer 1 got closer to this boundary, it detected a shift from solar wind to the medium between stars, providing important information about the structure of the heliosphere and its contribution to Earth's protection from cosmic radiation. The spacecraft revealed a distinct boundary known as the termination shock, where solar wind slows down and becomes denser. Beyond this boundary lies the heliosheath, where the solar wind interacts with the interstellar medium, creating a complex and dynamic environment. Explorer 2's journey has also made a significant contribution to our understanding of the outer solar system. Its flybys of Jupiter, Saturn, Uranus, and Neptune provided crucial data, especially its evaluations of Uranus's magnetic field, which was found to be tilted in a way that challenged existing models of planetary magnetism. These discoveries have sparked further investigations into the magnetic fields of other planets. These missions have not only expanded our scientific understanding but have also sparked public interest in space exploration. The stunning images of distant planets, along with the personal stories behind the spacecraft's missions, have inspired millions worldwide. The breathtaking images of Saturn's rings and Jupiter's volcanic moons have become iconic, encouraging the next generation of scientists and explorers. As the Voyager and Explorer missions continue to send back groundbreaking data, the ongoing exploration of space between stars presents unprecedented opportunities to understand the very fabric of the universe. While the focus has traditionally been on the planets within our solar system, the shift towards studying interstellar space has revealed some surprising insights about the regions beyond the Sun's influence. These areas, once thought to be empty voids, have proven to host complex interactions and phenomena, some of which challenge established scientific models. One of the most fascinating discoveries made by the Voyager spacecraft is the detection of the origin of cosmic rays from outside our solar system. These high-energy particles, moving through space at nearly the speed of light, offer clues about processes occurring in distant regions of the galaxy. By studying the energy and composition of these cosmic rays, scientists hope to gain a deeper understanding of the mechanisms operating in faraway stellar nurseries and the dynamics of galactic environments. In addition to Voyager 1 and Voyager 2 venturing further into interstellar space, their instruments continue to monitor the density and movement of the interstellar medium, the matter that exists between stars and a galaxy. This medium, composed of gas and dust, interacts with the solar wind in a way that affects the shape of the heliosphere, the protective bubble created by the Sun's influence. As the spacecraft approach and pass through this medium, they are providing crucial data that will allow scientists to better model the behavior of matter and energy in the vast spaces between stars. In addition to exploring the medium between stars, the Voyager spacecraft have made major contributions to our comprehension of magnetic fields in our solar system. Both Voyager 1 and 2 have provided detailed measurements of magnetic fields in interstellar space, revealing aspects of the nature of these fields and their role in shaping the surrounding environment. These findings may lead to breakthroughs in our understanding of the behavior of magnetic fields in other galaxies, contributing to a broader understanding of the cosmic forces at work across the universe. The ongoing exploration of the outer regions of the solar system and beyond is not only expanding our understanding of space but also inspiring future generations of scientists and engineers. The iconic images taken by the Voyager spacecraft, including the famous pale blue picture showing Earth from a distance of over 6 billion kilometers, serve as a reminder of humanity's place in the cosmos. These images, coupled with the scientific discoveries made by the spacecraft, have had a profound impact on how we view our planet and our relationship with the universe. The accomplishments of these missions have also paved the way for more ambitious future projects in space exploration. With the technological advancements made during the Voyager and Explorer missions, the possibility of sending even more advanced spacecraft to the farthest reaches of space is becoming increasingly feasible. Missions to distant exoplanets, the search for habitable worlds, and the exploration of other star systems are no longer just dreams, they are now realistic goals for the future of space exploration. Additionally, the information gathered by these spacecraft has far-reaching implications for understanding the conditions necessary for life to exist. By studying the composition of distant moons and planets, scientists have discovered valuable insights into the factors that contribute to habitability, such as the presence of water, atmospheric conditions, and a wide range of organic molecules. Not only do these findings support our search for life elsewhere in the universe, but they also deepen our understanding of how life on Earth may have originated. The collaboration between scientists, engineers, and institutions around the world in these missions demonstrates the power of global cooperation in the pursuit of knowledge. As the Voyager and Explorer spacecraft move forward with their journeys into the unknown, they carry with them not only humanity's hopes and dreams, but also the collective spirit of discovery that drives us to explore the farthest reaches of the cosmos. The anomalies detected by Explorer 1 and other spacecraft also highlight the importance of continued vigilance and adaptability in space exploration. As technology advances and new discoveries are made, it is essential to remain flexible in how we interpret data from these distant spacecraft. The strange signals that have recently been detected could represent new and unexpected phenomena never before witnessed, pushing the limits of our comprehension. In conclusion, the investigation of space travel is a never-ending journey that continues to reveal new mysteries and challenges. The discoveries made by the Voyager and Explorer missions have reshaped our understanding of the solar system, interstellar space, and the universe as a whole. As these spacecraft continue their long journeys beyond the reach of human observation, they will undoubtedly continue to provide invaluable data that will shape space exploration for generations to come. The legacy of these missions will endure, inspiring future explorers to venture into the unknown, driven by the same curiosity and desire to comprehend the universe that propelled humanity's space exploration efforts from the very beginning. As humanity stands on the threshold of a new era in space exploration, the lessons learned from the Voyager and Explorer missions serve as guiding beacons. Their longevity, durability, and ability to transmit data across billions of kilometers have set engineering standards that current and future missions strive to match or exceed. These pioneering spacecraft have proven that even with limited technology by today's standards, the spirit of scientific inquiry can overcome seemingly insurmountable distances and challenges. Looking forward, the knowledge gathered from these missions is being directly applied to the design of next-generation probes and space observatories. Missions like the James Webb Space Telescope, the planned interstellar probe concept, and other deep space endeavors build upon the foundation laid by Voyager and Explorer. These future missions aim not only to observe but to interact with their environments in more sophisticated ways, using artificial intelligence, advanced propulsion systems, and autonomous navigation to venture even farther into the unknown. Furthermore, the data relayed by Voyager and Explorer have influenced disciplines beyond astronomy and astrophysics. Insights into radiation, particle behavior, and the mechanics of space environments have implications for designing safer human space travel systems. As we prepare for manned missions to Mars and potentially even to moons of the outer planets, understanding the interplanetary and interstellar environments becomes critical for long-term survival and success. Public interest continues to be a powerful driver for exploration as well. The awe-inspiring stories and images shared through Voyager's journey have captured the imaginations of students, artists, scientists, and dreamers across the globe. Educational initiatives and outreach programs often use these missions as a cornerstone to inspire learning in science, technology, engineering, and mathematics, STEM, ensuring that the next generation remains engaged in our quest to understand the cosmos. Culturally, the Voyager spacecraft have taken on a symbolic role. The golden records they carry, containing sounds, images, and music from Earth, stand as a message in a bottle cast into the cosmic ocean. They reflect not just our scientific achievements, but also our humanity, our languages, our music, our greetings, and our hope that we are not alone. As these silent travelers drift ever farther from Earth, they represent a profound truth. The drive to explore is deeply embedded in who we are. The need to ask questions, to seek out the unknown, and to connect with something larger than ourselves is part of the human condition. Voyager and Explorer have become timeless ambassadors of that spirit. And while their signals will one day fade and their journeys may continue in silence, their legacy will echo through every mission that dares to follow. They remind us that even the smallest launch from a distant planet can carry with it the biggest dreams, and that, from one tiny pale blue dot, great wonders can be born.